Well, in Chapter 4, Section 2, we're going to start off with the following question. Consider the function f of x, where x is the height above sea level, and f of x is the percent oxygen compared to sea level. From observation, we know that at sea level, the percent of relative oxygen is 100%. At 5,000 meters, it decreases to 50%, and at 8,900 meters, it is 30%. So the first thing we want to do is write the above three data points as ordered pairs, not changing our percents to decimals, so we are going to graph the actual percent, and then we are going to plot them on this graph that we have below. All right, so our first ordered pair is actually the trickiest one. So our first ordered pair says at sea level, we have 100% of our relative oxygen. So what is the altitude at sea level? Well, it would be 0 meters, and we would have our output as 100%. Our second ordered pair says when we are at an altitude of 5,000 meters, we then decrease to 50% oxygen. And then our last ordered pair says that at 8,900 meters, the oxygen level decreases to 30%. So we're going to graph each of these pairwise and then connect the dots with those lines. So our first one is at 0, we have 100%, and then at 5,000 meters, we are at 50%. So if I connect the dots, that gives me the line through those 2 points. So my next pair that I'm going to do is 0 and 100, and 8,900 and 30%. So 8,900 is almost 9,000, and it's up at 30%. So now I connect these 2 lines, and I get something that looks like this. So the last pair is going to be 5,050 and 8,930. So I go to 5,000 and I go to 50, which is here, and 30, which is here. And if I connect these 2 lines, for these 2 points, I get a line that looks like this. So I now have 3 different graphs, right, corresponding to the pairs of points for each of these, right? Would it be possible to draw one line that contained all 3 of those points? And the answer is no, right? Because they don't lie on a straight line. So if I wanted to use a line to model the air, the percentage of relative oxygen at a height, I could ask the question, which one of these 3 lines is going to be the best model? The orange one, the red one, or the green one? All 3 of them contain 2 of the 3 data points, right? But which one's going to be the best way to determine how much oxygen is available at any altitude? Well, that's an important question, because in real life, when we encounter data, when we do science, the first part of the scientific process is to go out and gather data. And then what do? We try to come up with a hypothesis, aka a model, that is going to determine what we have. So in this case, we would have 3 things we'd want to determine, well, which one of these is the best model? Well, if you were doing the scientific process, you would then go back out into the field, gather some more data points, and then check them versus each of these to determine which one is the most accurate. It turns out that from the mathematical side, there is a way for us to try to, quote unquote, determine which line is best. And so we're going to start that process now. It's going to be something that we're going to continue next time, and that is one of the reasons we're going to be needing our graphing device next time, is we're going to be using it in order to help us determine which line is going to be the most accurate. Okay, so now we have a couple of these lines. So now, part B says, use the points from part A to find the slope of each of these three lines. And what does the slope represent? Okay, so let's go back. We're going to find the slope of each of these lines. So let's start off with the red line. So our red line contained our first two ordered pairs. So its slope is going to be m is equal to, and our two ordered pairs were 0, 100, and 5,050. So 0, 100, and 5,050. So if we were to find our slope, m is equal to 100 minus 50 all over 0 minus 5,000, which gives us negative 50 over 5,000, which is going to reduce to negative 1 over 100. All right, so our slope for the red line is negative 1 over 100. The next line that we did was our green line, and it had the point 0, 100, and 8,930. So we find the slope of our green line, so m equals 100 minus 30 all over 0 minus 8,900. And let's see, alpha y equals, to get our fraction, 100, take away 30 over 0 minus 8,900, and we get negative 7 over 890. And then lastly, we have our orange line, which used the points 5,050 and 8,930. So our slope for that line is going to be 8,900, take away 5,000, all over 30 minus 50. So 8,900, take away 5,000, all over 30, take away 50, and we get but I did that upside down. So let's type that in right. Oh my. Let's try again. Y2, so 30 minus 50 all over 8,900 minus 5,000. So now if we do that properly, we get 30 minus 50 over 8,900, take away 5,000, and we get negative 1 over 195. So just to help us out, this is, well, this one's exact actually, is equal to negative 0.01. If we go negative 7 and we divide that by 890, we get negative 0.0078, so about negative 0.0079. And for our last one, if we go 1 over 195, we get negative 0.0051. So we notice all of the slopes for the different points are different, right? We have negative 1/100th, negative about 7.81 and then 5/1000ths, approximately. All right, so we keep going now, and part C says, find the equation of each of these lines. Use each equation to find the zero of the linear function, and what does it mean? All right, so I don't think we answered the what does it mean for part B. So let's head back to that part for 1 second before we do this. So what is it that the slope represents? Well, by definition, slope is the change in y over the change in x, right? So it's the change in percent oxygen divided by the change in meters above sea level. So what does that mean? For each meter that you go up, it tells you how much of a percent of oxygen you are losing, right? So for each meter you go up, you're in the first 2 points, you're losing 1/100th of a percent of oxygen. In the second one, you're losing about 8/1000ths of a percent of oxygen, and in the orange one, you're losing about 5/1000ths of a percent of oxygen per meter. So that's what our slope represents. Part C, find the equation of each of these lines. Use each equation to find the zero of the linear function, and what does it mean? All right, so in red, that's going to be our easiest one. We have our slope, m is equal to negative 1 over 100. And this one, we actually know the y-intercept. The y-intercept is 0, 100. So that gives us the equation of the line is y equals m, which is negative 100x plus 100. All right, in green, we have our slope. This one's also pretty straightforward. Our slope is negative 7 over 890. And we're also using the y-intercept of 0, 100, right? So the equation of this line is y equals negative 7 over 890 plus 100. And lastly, we're finally to the orange. This one we're going to have to do a little more work. We have m is equal to negative 1 over 195, but we're not using the y-intercept this time. So we're using the point 5,050, and as we discovered in the previous section, if we use the other point, we're going to get the same answer. So if you want to use 8,930, by all means do so. It's not going to change anything. So this time we do y minus y1, so y minus 50 is equal to m, which is negative 195, times x minus 5,000. So we get y minus 50 is equal to negative 195x, then we distribute the negative 195 or over 195 into our fraction. So times our negative 5,000. And we get 1,000 over 39. And then we need to add 50 to that. So plus 50. And we get 2950 over 39. So y equals negative 1 over 195x plus 2950 over 39. So those are each of our three equations. So let's go ahead and put each of these into our graphing device and see what we get. So let's go with our first one is negative 1 over 100. X plus 100. Our second one is negative 7 over 890. X plus 100. And lastly, we have negative 1 over 195. X plus 2950 over 39. And we're going to graph, and it's not going to show us anything because our window is all messed up. So let's take a cue from our graph here, and we see our axes look something like this. So let's go from 0 to about 15,000 on the x, and we're going to go from 0 to 100 on the y. So we go window. We're going to make our x-min, I'm going to go negative 1,000 to give myself a little breathing room. I'm going to go out to 19,000 to make sure it fits, and then I'm going to scale in the thousands. I'm going to make my y-min 0. I'm going to make my y-max, let's give ourselves a little room here. Let's make our y-min negative 10. Let's make our y-max 110. And let's go ahead and scale this thing in tens. That's our red. This one's going to be our green. And this guy is our orange. So each of them have intercepts. And what is it that the x-intercept is going to represent this time? So when our graph crosses the x-axis, what does that represent in this picture? Well, what is the y value on the x-axis? Well, what does the y value represent? It's the percent oxygen. So when our graph intersects the x-axis, it's telling you the altitude above sea level where there is 0% oxygen. We can use our graphing calculator to find those zeros. So we go second and calculate, and we want to find our zeros. So notice in the top part of my calculator right here, it says y1. Well, y1 is my red graph, so let's find it. So am I to the left of my 0? I am. Now I move my cursor to the right, so I go below, hit enter, and then I move back and say guess. And it tells me that the 0 for the red graph is at 10,000 meters. So note, we could have also gotten this by just setting our y equal to 0 and solving. If we go 0 equals negative 100 x plus 100, if I solve this equation for x, I minus 100, I minus 100, gives me negative 100 equals negative 1 over 100x. I then multiply both sides of the equation by 100, or negative 100. So negative 100 times negative 100 is 10,000. Positive 10,000 is equal to x, which is the same number we got here, right? Because we were finding the x coordinate when y was equal to 0. That's how you find x-intercepts. We can do the same thing again on our calculator, but this time it got a little crowded at the bottom. So I'm going to go back to window this time, and I'm going to make my y-men a little bit smaller. I'm going to take it all the way down to negative 40. So that I can see on the other side a little bit better. It's not going to change the numbers, just the picture. So now I want to find the 0 of my second function. So I go second, calculate 0, but this time I don't want to do y1. So I press my down arrow, and notice that my calculator now says y2, and it shows its equation in the upper left-hand corner. So now when I go second, calculate 0, instead of moving along, second, calculate 0, I move down, I press my down arrow to go to y2. I'm still to the left of my 0, so I hit enter, and now I move to the right of my 0. Hit enter, and then I move back guess. And this time it tells me 12,714 meters approximately. And lastly, we're going to do the same thing. So second, calculate 0. Hit my down arrow twice this time to get to y3. First curve to the left, move to the right, press enter, and then back to my guess. And this time I get the 0, 14,750. So for each of them, it tells me 3 different heights. And we'll notice, depending on which model we used, there's almost 5,000 meters difference on when we would run out of oxygen, right? 10,000 meters, 12,714 meters, and 14,750 meters, right? So it once again circles back to the question, well, which one of these is the best model for our oxygen? So if we go back to our calculator and we go second table, and we want to look at it, right now our table's not very usable because our x is counting in ones, which isn't very helpful. So you'll notice that on the bottom it says, press plus for delta table. If we press our plus key, we can then change what our x's are going to change by. So if we look at our original graph, what are our x's changing by? Thousands. So that seems like it would be a good way to look at it. So we change our delta x to 1,000. And now we can see our percents oxygen and so forth when we look at them in our table. So we'll notice in this, they're very hard to read because it's giving us fractions. If we want to force our calculator to put decimals in our table, we go to y equals, and we use our arrow until we get to the right of what we have here. We press math, and we take choice number 2, and we say, please give me decimals. And we can do the same thing once again. Scroll to the end, math, choice number 2 for decimal. And lastly, we do the same thing here. We get to the end, and we go choice number 2 for decimal. So now when we go back to our table this time, we can scroll over and we get our different percentages. So notice when we compare our different models here, y1 and y2 say at an altitude of 0 meters, how much oxygen do we have? 100%. But when I look at y3, how much oxygen does it tell me we have at 0 meters? 75%, right? Oh, that's interesting, because we know that's incorrect. If we go down to 5,000 meters, we'll notice we know at 5,000 meters we have exactly 50% oxygen. Model 1 agrees, Model 2 says we have 60, and Model 3 says we have 50. So this time it's Model 2 has the error. And if we get down to around 8,900, so 9,000, Y1 says we have 10% oxygen, Y2 says we have 29%, and Y3 says we have 29%, when the actual answer is 30%. We're pretty close. So we notice each of these lines has errors in the approximation. So the philosophical question then is, well, is one of these lines the best model? And if so, how can we rank and compare which ones are better? Because our goal is to come up with accurate models. And we know that none of these are 100% accurate, so which one's the best, right? So that's going to take some definition, because we have to quantify, well, what does it mean to be the best line that approximates a data set? And how can we measure that? Because it's not a quality judgment, right? We want to have an actual scientific measure that allows us to determine which of these things is going to be the best. All right. So we are going to take a break from that and switch to our next example. So example, you know what? All right, so we're here where we've got some zeros below this first 3. We've got some zeros above and below this 3 in the middle. Our goal now is to get rid of these zeros that we have, or these digits right here, and make them 0. So our last equation, so row 3 is negative 55 equals 13. And at this point, we don't want to divide by negative 55 to make that a 1. If we do, we're going to introduce decimals and fractions, which is going to make this thing a holy mess. So we're going to keep working using similar things. We want to eliminate the 8, and we want to eliminate the negative 7. So if we come over here, we can do 55 times, or 8 times row 3, plus 55 times row 1 to replace our row 1. So to do that, remember, we come down, we select our region here, so we have to group select that entire 4-cell row, and then we come up here, we put our formula in, and we're going to put in what we have there. So we want 8 times, and then our row 3 is going to be A15 colon through D15. So we get it highlighted, plus 55 times our row 1, which is going to be A13 through D13. So A13 through D13. And we press enter, or Control-Shift-Enter rather, and we get this. All right, and then row 2, we're now going to do something similar. So I'm going to have to do -7 times row 3 plus 55 row 2, and that will be to replace row 2. Oh, I forgot my quotes. So -7 times row 3 plus 55 times row 2. There we go. When we come down, we select our region, Shift left click, and then we come up here and we go Enter. And this time we want to go -7 times, our row 3 is still A15 through D15. And then we're going to add to that 55 times our row 2, which is A14 through D14. And Shift Control Enter, and we get the following value. And then lastly, our row 3 isn't going to change, so we're going to have that this is equal to A15 through D15. So now that we've done this, it gives us our final set of equations. I'm just going to copy this whole thing over into our notes for now. And so that was actually this system of equations is what we started with, was the one from U Try 1. So then this right here would represent the equation 165x equals 654. It would be -165y is equal to 459. And the last one says that -55z is equal to 13. So we could then solve for each of those variables by doing the appropriate division. So x is 654 over 165. Y is -459 over 165. And z would be -13 over 55. And that would be all of our solutions to that system. So we can use Excel to do these operations. And I know some of you may be familiar, they can also be done with a TI calculator, and if you know that method, that's fine as well. But Excel is going to be a little more general than what you can do on a TI graphing calculator, as we'll see. There's more options, let's put it that way, in Excel. Plus, most of the time in real life when you're at work, you're probably not going to have a TI calculator issued to you, but you will have Excel on your computer at work. So these are things that we're going to want to be able to do. All right. Let's move back to what we were just doing. So I want you guys to rewrite this matrix as a linear system. All right. So if we look at our first row, what equation is that going to be? Well, we have our x column, our y column, our z column, and our constants. So if this is going to tell us that x is the same as -7, the second row is going to tell us that y is the same as 6, and the third row is going to tell us that z is the same as pi. So then, when we have a matrix that's in this form, it actually just tells us exactly the solution, which would be -7, 6, and pi, right? So matrices that are in this form are going to have a special name. So let's look at some of the characteristics of this matrix that we were just working with. So these elements right here are all 1. So these elements are on the main diagonal. So the main diagonal is the entries that are in the same row and column. So for instance, in this matrix, this first entry, the first one, is in row 1, column 1. The one in the middle right here is row 2, column 2, and this is one right here is in row 3, column 3. So the main diagonal are the entries whose column and row number are the same. So first row, first column, second row, second column, third row, third column, and so forth. So when we have a matrix, what's on the main diagonal is going to be helpful. So if we look back at the previous example that we did in Excel, we'll notice that these were our main diagonal entries, and everywhere above and below it, we were able to get to 0 by doing certain row operations. If we go all the way back to example 2, this one's a little bit different, right? So we look at our main diagonal. I have a 1, but then on my main diagonal, instead of a 1, what do I have this time? I have a 0, and I have a row of all zeros. So something interesting happened here. In example 2, when I rewrote this as a system of equations, I ended up with an equation 0 equals 0. And we would end up with an infinite number of solutions. In this example that we did in Excel, when we had numbers on the main diagonal and zeros above and below, we got exactly one solution. In the example you just did, when we had ones along the main diagonal and zeros above and below, what did we get? Exactly one solution. So the main diagonal is going to give us information about the type and number of solutions. So remember, if we go back to 4.1, every linear system, no matter how many dimensions it's in, will always be one of these three things. Where there is no solution, exactly one solution, or there is an infinite number of solutions. So based on what we've observed, when we get ones on the diagonal, or numbers along the main diagonal, and zeros above and below, it's going to put us in this case where we have exactly one solution. If we don't have ones along the main diagonal, we're either going to get no solution or an infinite number of solutions. And we'll talk about how we can discern between those cases. All right. So that gives us our next definition that we need to talk about, which is row echelon form and reduced row echelon form. So a matrix is in row echelon form if the following three things are true. The first non-zero entry in each row is 1. The leading one of any row is further left and that means the column number is less than the leading one of all rows below it. And 3, any row or rows of all zeros are at the bottom of the matrix. So for something to be in row echelon form, it must satisfy these three things. The first non-zero entry in each row is a 1. The leading one of any row is further to the left than the leading one of all rows below it. And any rows of all zeros are at the bottom of the matrix. So let's leave ourselves a little space. We're going to come back and add something here. And then we want to look at our example 3. So example 3 says, determine if the matrices are in row echelon form or reduced row echelon form. We haven't talked about reduced row echelon form yet, so we're just going to focus on REF. And these are our three properties. So let's start with matrix 1. So the first property is the first non-zero entry of every row a 1. So I check row 1, first entry is a 1. First non-zero entry is a 1. Check the third row, 0, 0, 0. First non-zero entry is a 1. So it passes our first criterion. The second criterion says the leading one of any row is further left than the leading one of all rows below it. Okay, so here's my leading one in row 1. Is it further to the left than all the leading ones below it? So leading 1, yes. So then I check my next leading one. Is this further to the left than all the leading ones below it? Yes. And then the last one is vacuously true since there's no leading ones below it. It's further left than all the ones below it. So we pass 2, and then 3 is not applicable. It says any row or rows of all zeros are at the bottom of the matrix. So this doesn't have any rows of all zeros, so it also passes. So this matrix is in row echelon form. All right, let's check our matrix in the middle. Is the first non-zero entry of every row a 1? So 0, 0, 0, 1, check. 0, 0, 1, check. 0, 1, 1, 1, check. So it passes 1. We now go look at number 2. The leading one of any row is further to the left than the leading one of all rows below it. So here's my leading 1. Is it further to the left than the leading ones below it? No. So this fails too. So this one is not in row echelon form. All right, lastly, we look at our third matrix. Is the first non-zero entry in every row a 1? So 1, 0, 1, check. 0, 0, 1, check. So it passes 1. 2, is the leading 1 further to the left than the leading one of any row below it? That one passes. Row 2 passes. Row 3 passes. So we pass 2. And then 3, does this matrix have any rows of all zeros? And the answer is no. So this one passes as well. It is also in row echelon form. All right, so let's pop back up here. We're going to add our one thing for reduced row echelon form. Or RREF has all of the same 3 row properties, but it also has a 4th column property. So all the entries above or below a leading 1 are 0. So the difference between row echelon form and reduced row echelon form is any leading 1 has to have only zeros above and below it. So now let's go check example 3 again for RREF. So since reduced row echelon form has all the properties of row echelon form, we don't have to check the matrix in the middle, because if it's not row echelon form, it's impossible to be reduced row echelon form. So now let's check our first one. We look at our first leading 1, are all the entries above and below it 0. So the first column passes. We look at the second column, are all entries above the leading 1 0? Are all entries below the leading 1 0? So the second column passes. This column doesn't have a leading 1, so it passes. We finally get this leading 1. Are all the entries above and below it 0? No. So this fails 4. So this one is not RREF. So we know this one automatically fails, because if it's not REF, it can't be RREF. So then our last one, we look at our leading 1s, are all entries above and below these 0? So above and below 0, above and below 0. Here's my third leading 1, all the entries above it are 0. So this one passes. So this one is in reduced row echelon form. So notice, in this example, our matrix is in reduced row echelon form, and it would tell us exactly what the solution to that linear system would have been. So we're going to solve this example, and to do so, we are going to do the following. So let's outline our steps. So step one is we're going to write the system as an augmented matrix. So our first column is 1, 4, 3. Our second column is -2, 2, 3. Our third column is 3, -3, -1. And our fourth column is 11, 4, and 4. So our size of our matrix is going to be a 3 by 4. So now step 2 is we're going to use Excel or a TI-84 to RREF the matrix. So what we did before in Excel basically was reducing the matrix to reduced row echelon form. So we last time, and then at the beginning this time, did it in Excel. So this time I'm going to show us how to do it on our graphing calculator. So the first thing we're going to do is we need to enter our matrix into our calculator. So to do so, we press our second key, and then the X inverse is secondary function is matrix, and it should pull up a menu that looks like this. We then need to go over to Edit. So we go over to Edit, and I'm going to choose to edit matrix A. And the next thing we need to do is put in our size. So it's the rows by the columns. So we have 3 rows and 4 columns. So we go 3 by 4. We then just type our entries in. So 1, -2, enter, 3, enter, 11, enter. Put in row 2, 4, 2, -3, and 4. And then lastly, I'm going to put in row 3. So 3, 3. I wrote a Z because I'm apparently crazy today. That should be a -1 because the coefficient is 1. -1 and 4 once again. So now we've got our matrix entered into our calculator. So we go second quit to get back to our home screen. And then we need to get back into our matrix menu. So second matrix. This time we want to do some math with our matrix. So we're going to move over to math. And then we're going to scroll down about 13 times until we find RREF, which stands for reduced row echelon form. Then we go second matrix again. And now it's on names. We're just going to select our matrix A. You'll notice that matrix A now has a size associated with it, 3 by 4. Close our parentheses and press enter, and our calculator reduces that matrix to reduced row echelon form for us. So since our matrix is in reduced row echelon form, so since the matrix has 1s on the main diagonal, the solution is column 4. So we have our 1s on the main diagonal. So our system of equations really is x equals 3, y equals -1, and z equals 2. So our solutions are really just column 4. So it tells us what x, y, and z are. So x, y, z is equal to 3, -1, and 2. So that would be the solution to that linear system. So when we get 1s on the main diagonal when we do RREF, that's the best case scenario. When that happens, we get exactly one solution, and the solution is whatever the entries are in column 4. So that's the optimal situation. Unfortunately, it's not always going to be that way. So let's try our next example. We're going to do the same process this time. So the first thing we need to do is write our linear system as a matrix. So 3, 2, 4, -4, -1, and -7, -1, 1, and -3, and 6, -1, and 13. This is still a 3 by 4 matrix. Let's go back to our calculator. So we go second matrix. We go over to edit. It's still a 3 by 4 matrix, and now we're just going to type over all of our entries. So 3, -4, -1, and 6, 2, -1, 1, and -1, 4, -7, -3, and 13. So we've got our matrix entered. So then we go back to our matrix menu, down to RREF. Second matrix, we select A again. And we get the following output from our calculator. So our matrix, once again, is in reduced row echelon form, but it's different. So the first thing we're going to notice, we don't have 1s on the main diagonal.
Professor?
Yes, ma'am. All right, so we notice the difference this time is we don't have 1s on the main diagonal. So row 3, column 3 is not 1. The matrix does not have 1s on the main diagonal. When this happens, it's the other two possible cases. So when we had 1s on the main diagonal, we get exactly one unique solution. So this is going to go down in one of two ways when there's not 1s on the main diagonal. So we're going to get the first case, case 1. There are rows of all zeros. So if we were to write out this system, what we would have is x plus 0y plus z is equal to -2. We would have y plus z equals -3. And row 3 would tell us 0 equals 0. Well, that's true, right? So this tells us that there's an infinite number of solutions. So we're going to let z equal the parameter t. So it's worth noting, we picked z for the parameter, because column 3 did not have a leading 1. So in our matrix, we had a leading 1 in the x column, we had a leading 1 in the y column. We did not have a leading 1 in the z column, right? It was missing. That means z is going to be our parameter. So in general, any column that is missing a leading 1 is going to be a parameter in your solution. So then that gives us the following set of equations. We're going to have the two equations, and we're going to solve them for the non-parameter variable. So x plus t equals -2, and y plus t is equal to -3. We're going to solve for the variable in each equation. In each equation. So we need to solve this for x. So we minus t, and we get x equals -t minus 2. And then our other equation is y plus t equals -3. And we minus t, we get y equals -t minus 3. So the solution is x, y, z. But remember, z is our parameter. X is -t minus 2. Y is -t minus 3. And z was our parameter, t. This is a solution for every real number t. So if you picked t to be 55 and plugged that in, it's going to generate an ordered triple that is a solution to that system of equations. All right. All right, so let's go ahead and do this. So I've already put my matrix in, so just to verify, 3, -4, 2, 6, 1, 2, 3, 9, 4, -2, 5, and 0. So then we're going to RREF that thing, and we end up with a matrix that looks like this. So a couple of notes I do want to mention. We ended up with decimals, and most of the time that's okay, but sometimes you do want fractions. In the event that you do, you can convert all of the entries in a matrix to fractions by pressing our math key, choosing the first choice fraction, and pressing enter again, and it will take and convert all of those decimals to fractions if it is possible. All right, so after RREFing this thing, we notice that we are in a similar situation to the previous example. I don't have a 1 on the main diagonal, right? So just like what happened up here, row 3, column 3 doesn't have a 1 on the main diagonal. But this case is a little different. If I write out my equations, I have x plus 8/5 z is equal to 0. I have y plus 7/10z is equal to 0. But my last equation says 0 equals 1. That's false. So when this happens, this is case 2. We get no solutions. So case 2, if a row is all zeros except for the last entry, then the system has no solution. So just to summarize the two possibilities, so in the case where we don't get ones on the main diagonal, we're going to get something different. If we get ones along the main diagonal, then the solution is just the last column, right? And we're done. If we don't get ones along the main diagonal, and the rows consist entirely of zeros, then we're going to get an infinite number of solutions, and we're going to need to parameterize. In the case where we don't get ones on the main diagonal, once again, case 2 is where we get a row, but instead of being all zeros, it's zeros everywhere except for the entry in the last column is 1. That gives us the equation 0 equals 1, which is false. And then we get no solution. So that's how our three cases are going to break down. All ones on the main diagonal, we get one solution. If we don't have ones on the main diagonal, it's either infinite solution or no solution. We get an infinite solution when our rows consist entirely of zeros. We get no solution when our rows are all zeros except for the last entry. That's how it's going to work when we do reduced row echelon form. All right.